Hi, my Technicide fam. Video 4 in the CSEC Physics Formula book starts now. In this one, we're looking at the moment of a force. So let's start off as usual with a definition of moment. The moment of a force is the turning effect of that force about a point. In another way, we could say it is the product of the force and the perpendicular distance of its line of action from the point. So here we go. I have a nut here. I want to turn it. I want to open it. So of course I'm going to be using this spanner. Now if I put my hand at this point and apply a force in this direction to turn it, so I'm pushing down on the spanner, then to determine the moment of this force, meaning the turning effect of this force, how much turning this force will give, I would need to consider the perpendicular distance from the point. Where is the point? So let me just label force. Now I'm going to be showing you where the point is. Now in this example, it would be at the center of this nut. Now if we consider turning the spanner in this direction, as in the example shown, the spanner will be turning. Now that is what the moment of a force is. It measures how much a force will cause a body to turn. And to complete this, we need to consider the perpendicular distance from the point, which is the pivot. Now in this case, as you can see in this little snippet, the center of the bolt would become our pivot. Now, as you can see, the spanner is turning. You recognize that it's pivoting at the center of the bolt. Now, when you're measuring the distance of the force, it should be the perpendicular distance from the point, which is also called the pivot, from the point where the object pivots to the point of application of the force. And so, because in this setup, the pivot is at the center of the bolt, then the distance is measured from the center of the bolt out to where the force is applied. So now let's continue. Forces can turn objects in two directions mainly. We have this beam, for example. So the first direction we're looking at is clockwise. Now in this setup, because the beam will be turning about this pivot, so it is free to turn in this direction and that direction, we'll be analyzing to see how we're getting a clockwise direction. So think of the face of your clock. It goes in this direction. So that is a clockwise direction, as long as it's turning in the same manner that a clock turns. So notice the beam was turned in the same direction that the clock hands would move. That is clockwise. And likewise, if I remove the force, the beam will return to its normal position, its rest position. Now the second direction is anti-clockwise. And for this one, I'll apply a force here. And now for anti-clockwise, what happens is it will turn the object in the opposite way to the movement of the clock. So in this case, it will turn the beam like that. And so that is opposite to how the clock turns, and so that's why we call it anti-clockwise. Remove the force and the beam will again return to its rest position. Some devices are designed based on moments. For example, a lever. A lever is any device which turns about a fulcrum, also known as a pivot. Now there are three classes of levers, and there are some key terms that I want you to bear in mind as we go through these classes of levers. So we're looking at load. Now the load is the force that you want to overcome. You want to lift it. You want to turn it. That's what the load is. The effort is the force or what you are putting in to turn or to lift whatever load is there. So load is external. It's what is already there and you're trying to lift it or to turn it. And then effort now is what you, the individual, is putting in. Fulcrum or pivot is the point about which the lever will turn. So let's look at this example. So this setup is showing a lever, a very simple lever, where you just have a piece of, you could have a piece of board here, and then you put an object under it that is acting as a pivot or a fulcrum, and then you have a stone on it here. Notice this is a very simple setup, just like you would have your seesaw, but only difference is the pivot is not in the center, as this example. So now let's identify the different parts according to the key terms. So we have the fulcrum here naturally because this is the pivot of the lever. This is where the lever will be turning about. When we say turning about, we simply mean it will be turning at this point. That's what we simply mean. Next point, we have the load. This is the rock that we want to lift. And then we have our effort, which we're going to apply up here. So we have our rock here that we want to lift, that's our load. And the effort will be the force we put in to lift this load. So let's look at what happens now as we apply a little effort. There you go. So you're seeing where by applying some effort, we were able to lift this beam with this rock. So now let's go look at the classes of levers. So we're going to first class levers. Now, an example of first class levers is a scissors, and I'm going to be showing you what type of levers are classified as first class. Of these three terms, the principle I use to remember first, second, and third class levers is I remember which of these terms falls in the middle. Like you're seeing effort, fulcrum, load. I remember which one falls in the middle, and that helps me to figure out the manner in which each class of lever operates. So for first class lever, F for first, we have F for fulcrum. The fulcrum of this lever is in the middle, and it lies between the load, and for a scissors, the load will be the paper or cloth that you're cutting, and the effort. So the first class lever, F for first, has F, the fulcrum, in the middle, and it's naturally between the load and the effort. So for this one, the effort for the scissors are being applied at the handles. The load would be in the scissors that you are cutting. Then we go to second class levers. And this one, an example of this is a wheelbarrow. And for this one, we have load in the middle. So for second class levers, we have the load between the fulcrum and naturally the effort. So for a barrow, the load would be inside the center part there. The fulcrum would be at the axle of the wheel, and where you hold the handles is where you would apply your effort. So for second class levers, the load is between the fulcrum and the effort. Third class levers, example of this, as simple as a broom. So yes, you have been using levers all your life and not recognizing it. So for the broom, which is in the middle, the effort is in the middle because when we're holding the broom, you know, you're holding that part of the broom and your hand is moving there, while the hand up top is acting as your pivot point. Awesome. And then the load is the rubbish or the trash that you're sweeping. So from this, I've come up with a little acronym that I use to remember the arrangement, and it is FLE. First class, fulcrum in the middle. Second class, load in the middle. Third class, effort in the middle. All right, so let's now continue. Symbol for moment, that is a capital T. Formula for moment. Moment of a force is equal to the force times the perpendicular distance. It's key that it's the perpendicular distance. In symbols, it's T equals F times D. Some instances you'll see F times S or F times X. Either one, as long as it represents moment and it's force times distance, then that is acceptable. SI unit of moment, that's the Newton meter. Now, an alternate unit for this, we can have Newton centimeter, and we can also have kilonewton meter. So now let's try some examples. Question 1 reads, what is the sum of the moments acting on the beam shown below? Give your answers in SI unit. First thing we do in these questions is to identify our forces. So we'll label F1, F2, so that it's easy to identify which one we're making reference to in our equation. Then I'm going to be converting these distances to meters. Since the force is already in newtons, I'm going to be converting that to meters because the question asks us for SI unit. Okay, so now I'm going to be finding the individual moments for F1 and F2 and then adding them together because we were asked to find the sum. And I give them the subscripts 1 and 2 to match the forces that we're working with. Now remember, the distance is the distance from the pivot. So F2 is 4 centimeters from F1, but it is 11 centimeters from the pivot, and that's the distance we use. So of course we would convert 11 centimeters to meters and we would get 0.11. Okay, so now we're adding T1 plus T2. So that would be the answer for the sum of the moments acting on this beam. Let's go to question 2. It says a force of 8 newtons is applied to loosen a bolt. Calculate the moment of this force in each example. So now in this example, we're going to be naming this F1 and this is going to be F2. Now notice this force is being applied upwards. So the beam would actually, the spanner would actually turn like this. So that's anti-clockwise. Likewise, this one would turn like that, anti-clockwise. So now let's work out the moment of each example. We were not asked to put it in SI units. So being that Newton centimeter is an alternate unit, then we can leave it as is. So we're going to say moment 1 is equal to F1 times the distance. And there we have our answers. So this now brings out an important point that I want to make for levers and how moments is applicable. Now, there are times when you may be at home and or your parents might be working on something and let's say they want to pull a nut and the spanner they're using is a little bit shorter, and so you'll see them trade it in to get a longer one. What a longer spanner does is it gives them more turning effect on that nut. If one is available, you can suggest they get a longer one so that they are able to apply greater turning. So remember, the moment of a force is a measure of the turning effect of that force about a pivot. So for the shorter one, It's the same force that was applied at a shorter distance, and the amount of turning was 120 newtons centimeter. For the second one, the amount of force was the same 8, but it was at a longer distance, and so you got greater turning. So the moment of that force was 200 newton centimeter. Very applicable. So now, of course, it's your turn. So these questions, I want you to try them. These are very applicable questions. So yes, part 4 is done. Next, we are going to be expanding a little bit more on moments by looking at the principle of moments. Please join me then for the next in this series. Remember, check the link below so that you can get the answers to the questions. Thank you guys for watching. See you next time.